The sun, as we know, has a blackbody spectrum. It's a blackbody with a temperature of 6,000 degrees, and it looks white. In general, the blackbody spectrum is sufficiently broad that anything with a temperature of a few thousand degrees, the sun, an incandescent lamp, such that the maximum is anywhere near the visible, will not create sufficient differences between the way it activates our green, blue, and red receptors to give us a great sensation of color. So the sun appears to us white. Remember, its wavelength of maximum emission is right smack in the middle of the visible spectrum in the green, and it makes a beautiful rainbow of colors. And here someone has laid out the solar spectrum line by line by line, so this is to be read like a book. It's a very detailed spectrum of the sun, and indeed there's a blackbody spectrum here centered on the green, but there are these gaps, there are holes, there are specific wavelengths along the spectrum in which there are holes. Something is eating. The blackbody spectrum is continuous. Something is absorbing the light at particular wavelengths. And this was a discovery by Fraunhofer in 1814. And a few years later, Kirchhoff and Bunsen discover that if you heat a tenuous gas, a gas under low pressure and very low density, then the gas will glow if you either heat it by burning or ionize it by passing a current through it. When the gas is sufficiently tenuous, the light that it glows with is actually not blackbody spectrum, but only discrete spectral lines. And Kirchhoff is the one who figured out the regularity that relates these two pictures, and let's see how that works. We have an incandescent light here, or if you want any black body, say a star, and like the sun. If you are looking at this star, then you will see in your spectrometer a continuous blackbody spectrum with the maximum emission determined by the temperature of the star. To the left is a cloud of tenuous gas, so low pressure, low density, and if you observe the emissions from that cloud of tenuous gas, you get this line spectrum that Kirchhoff and Bunsen discovered. There will be discrete wavelengths, discrete places. It's called a line spectrum for the obvious reason of its appearance. There will be discrete places in the spectrum where this cloud will emit. On the other hand, if you observe the continuous emitter, the blackbody, through the cloud, you will see the rainbow, the full continuous blackbody spectrum of the blackbody that's behind, and at precisely the same wavelengths where you saw emission, you will see absorption. In other words, an atom or a molecule is characterized by a specific set of wavelengths at which it can either emit light or absorb. Now, when you bunch a whole collection of atoms densely together, then these lines are broadened gradually as you increase the density, and eventually when the density becomes large enough, they merge into the continuous spectrum of a blackbody that absorbs all light at any wavelength and emits in a continuous blackbody spectrum. But if the density is low and the pressure is low enough, then you find discrete emission as well as discrete absorption. So these wavelengths are properties of the gases in the cloud that we're talking about. Naturally, this discovery was a huge boon to chemistry, because what it allowed Kirchhoff and Bunsen to do was to heat various gases, observe the emission line spectrum, and conclude, identify the wavelengths of emission with those from known atoms, known elements, and they could find the elementary composition, the chemical composition of the substance that they were observing. Thus was born the field of spectroscopy. And so as we've seen, observing the line spectrum allows you to identify. So you can go over, or an expert can go over the spectrum and identify that this line, and that line correspond to the wavelengths at which we know thrice ionized iron atoms absorb radiation. So the degree, the darkness of these lines, the amount of absorption indicates something about the concentration of thrice ionized iron, and so on and so forth. You can go through the solar spectrum and identify all the elements that are there. And then in 1868, an interesting discovery is made by Janssen and Lockyer Independently, they look at the spectrum of sunlight during an eclipse, and they discover a line in the yellow right over here in this region of the spectrum, and it does not correspond to any known element. And so, after some further checks, they decide that they have discovered a brand new unknown element, and since it was discovered in the spectrum of the sun, they name it appropriately helium. Yeah, the helium you put in your birthday balloons was first discovered to exist in the spectrum of the sun. We'll talk later about why it's so hard to find helium on Earth. But the first indications of the existence of such a substance were in the spectrum of the sun. So, observing the line spectrum of an astronomical object can tell us about its chemical composition. As we'll see, it can tell us a whole lot more about the object. A spectrometer is one of the most essential tools in an astronomer's toolkit, and we will keep coming back to the spectrometer as the class goes on.